So the van der Waals equation corrects for the idea that the ideal gas law is only meant for ideal gases, but most gases behave as real gases. So the van der Waals equation corrects the ideal gas law equation and takes into account how real gases behave. You're going to be given two variables that are listed there, A and B, and they are just plugged into the equation. The equation is given to you on the equation sheet. So let's first again write down our knowns. So it says calculate the pressure. So that's what you're looking for. Your pressure is your question mark. Exerted by 0.500 moles of Cl2 in a 1 liter container at 25 degrees Celsius. So we have N number of moles. So 0.5 moles. We have a volume of 1 liter. And we have a temperature of 25 degrees Celsius. Remember, you have to change all temperatures immediately to 298 Kelvin. You add 273 to turn it to Kelvin. So right now you have all the variables for a PV equals nRT for ideal gas law. The difference is these two values, A and B. This is saying that the pressure and the temperature are not at ideal conditions, so the behavior of the gas is going to be different. So this is where you have van der Waals. You know it's going to be van der Waals because you're going to be given these two, A and B. So the equation looks complicated. It's not. So I'm going to write it up. So it's P for pressure plus A, which is your variable given above, times N over V, moles over volume, squared, close that bracket, times volume minus number of moles times B, and that all equals nRT. So it's really just correcting for the pressure and volume here. That's what it's correcting for. From here, it's simply just plugging in and solving. It is a big, long equation, so I'm going to write it below here. So I'm just going to plug in all my variables. P is what I'm looking for, plus 6.49, which is my value of A, times 0.5. I'm just shortening all the givens, squared, close that bracket, times the value of the volume, which is 1, you just have 1 liter, minus N, again, the number of moles, and that's going to be times B, which again is given above, 0.00562, close that bracket. Correct, that's 0.05. Okay. And then it's going to equal just nRT, which is 0.5 times 0.0821, ideal gas constant, times 298. So really it's just about keeping yourself organized. Then you're just going to start multiplying, dividing, subtracting, adding to kind of condense everything. So when we condense this the first time, it's just going to be P plus 0.16225. I take it to a lot of decimals just so that you're rounding, you don't have major rounding errors. 0.09719. That equals 12.2329. Then from here, it's pretty easy to solve for P, which is going to be 10.964. And my unit for P is going to be in ATMs. And if you don't know why, remember that the ideal gas constant, 0.0821, is only for when the volume is at atmosphere.